Hello everyone. We start our discussions on Unit 8, Acids, Bases, and Salts with this video. I took this screenshot from the website PHET, and it's great. It contains a lot of simulations across physics, chemistry, and biology. Here they're showing the dissociation of a weak acid. We'll get to this in future videos. Since throughout the unit we will be dealing with Brønsted-Lowry type of acids and bases, I want to start there. Brønsted-Lowry acids and bases to memorize. The first thing is just a short introduction. At home, you have some acids and bases. Let's see. You might be familiar with vinegar. Vinegar is an acid. It uses acetic acid in water. You know that acetate is C2H3O2 minus, but when you make it an acid, you add a hydrogen. That's acetic acid. So vinegar is acetic acid. I think about a little bit below 5% in water. Acetic acid. Other types of acid, or another acid that you may be familiar with, is gastric acid. Your stomach acid. Gastric acid. That's actually a very strong acid, hydrochloric acid. In terms of bases, a base that you may have in your home is sodium bicarbonate. That is baking soda. NaHCO3. So this is a base. And the last base I want to talk about is ammonia. Those are some examples of acids and bases. Some of them are weak, some of them are strong. We'll get to that later on in the video. So what is a Brønsted-Lowry acid and base? Let's go over those definitions. Brønsted-Lowry. Let's start with the acid. Bl acid. That is a substance, molecule, that donates a proton. What is a proton? A proton is the hydrogen atom that is missing an electron. So it is charged, it is positive, H+. Okay, let's take a look at some examples. Let's do hydrochloric acid, gastric acid. And one way we could show this that usually HCl at standard conditions is actually gas when it's not dissolved in water. But when you dissolve it in water, and you could sometimes indicate that by drawing water over the arrow, it dissociates. Dissociates means that it breaks apart into its, oh, there it is, a proton, dissolved in water, so it's aqueous, plus the anion, chloride, again, aqueous. That is an acid. A Brønsted-Lowry acid, because it donated a proton. But you want to be familiar with other forms of, or other ways that people can draw acid-base reactions. I'm going to take the same hydrochloric acid, gas, and we're going to bubble it into water, liquid. Is there a big difference between this first reaction and the second one that I'm about to draw? A little bit, because now this HCl is going to donate the proton to a partner, to water, and changing water to H3O+. So that's called, you might remember from your polyatomic ions, hydronium. It's still the same reaction, and it still tells you the same pieces of information. that HCl is an acid. It donates a proton. Now we don't literally see H plus because that H plus was picked up. It was picked up by water. So again, you want to be flexible when you look at these acid-base reactions. Be prepared to see them in different formats. Let me show you a Brønsted-Lowry base. Well, if an acid donates a proton, the base accepts a proton. Now, you know what? We're going to use this example here because we do have a substance that accepts the proton. It's actually water. This is the base. So I'm actually partial to this type of acid-base reaction because it literally shows an acid and base. So I like this format. This is fine. It's perfectly accurate, but I like this format because it shows an acid-base reaction, an acid-base pairing. Because it shows explicitly an acid-base pairing. Okay. All right. Let me give you another example of a base. Let's do ammonia. We talked about this in part A, NH3. Well, what's happening here? NH3, again, if it's pure, it's going to be a gas, but we bubble that into water, H2O. And don't worry, sometimes I use a full arrow, sometimes I use an equilibrium. We'll talk later. That's to indicate strong acid, strong base, weak acid, weak base. So we have an equilibrium, so it's not going to go completely to the products. And now what happens here is the base, NH3, accepts a proton and becomes ammonium. Plus, well, water donated its proton, so now it's hydroxide. So there's a lot of good polyatomic ion information that should be familiar. But first of all, let me label this. This is the base, and technically this is the acid. And these two are called ammonia. Oh no, ammonium. Ammonium. This is ammonia. This is ammonium. This is hydroxide. Hydroxide. Okay, so one last time, be prepared to see these acid-base reactions in different formats. Sometimes the water's written over the arrow. I like the ones where you literally see the acid and the base, like in these two examples. Okay. And you don't have to see the H plus, right? We don't have H plus here because it got picked up by water, but it still originally donated an H plus, therefore HCl is the acid. And definitely here, the base accepted a proton from water. Okay, so it's hooked up as an ammonium. So just be prepared to see acid-base reactions in different formats. Okay, moving on to part C. This is titled Acids and Bases to Memorize. There are 7 strong acids. Part C. Strong acids. And there are 7 of them. The first one is not a strong acid, so I'm going to put here, but I want to put it down because in comparison, its analogs are strong acids. You'll see what I mean in just a minute. HF. Hydrofluoric acid is not a strong acid, but HCl is. Not that, but yes, HCl. So HCl, we've seen this reaction already, plus H2O, arrow, not equilibrium, goes to H3O plus, plus Cl minus. So I'm not going to put the phases anymore. What's the pattern? Looking at your periodic table, these are the, what do they call these? The binary acids. Hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acid. But HF is not strong, but these three are. So those are our first three: HCl, HBr, and HI. These are the same. It's just the anion released is different. Br minus, I minus. So far, these three are strong. Three so far. What are the other four? The first one is nitric acid. The first one of the next four, nitric acid, HNO3, again, dump it into water, and it donates a proton, full arrow, H3O plus NO3 minus. The phases are aqueous and aqueous. Okay. Technically, when you write this out, this is also aqueous, and then it over time it dissociates into its ions. The next one is chloric acid. Chloric. So you do have to review some of your polyatomic ion material, and that is from chlorate. Chlorate is ClO3 minus, and then when you add a hydrogen, it becomes an acid. Let me put the phases, so we have at least one example where you see that it's proper to write this as aqueous as a reactant, but then over time, it's going to turn into aqueous. We have H3O plus again. Seems like that's a common theme with acids. Plus ClO3 minus, again, aqueous. The next one is perchloric acid from perchlorate. That is HClO4. Okay. Again, I'm not going to put the phases here. You've seen it already in this example, the second one. H3O plus ClO4 minus. The last one is a little bit tricky. It is sulfuric acid. Sulfuric acid. H2SO4. It's the only one that is diprotic. So this is a diprotic acid. It has two protons that can be donated. But when they talk about it being a strong acid, they're talking about it releases its first proton completely. So you do get one molecule of H3O plus for every one molecule of H2SO4, and you only lose one proton at first. So that is HSO4 minus. Okay. Now, it is true this can lose its proton to give us SO4 2 minus, but when they talk about sulfuric acid being a strong acid, they're really referring to the first proton being 100% released. So there's a definition. Strong acids dissociate 100%, or they fully dissociate. Let me see if I can put this into better words. Like over here, let's go back up to here. It's a strong acid because there's no equilibrium. You have 100% of the products. It's called full dissociation of the acid. Now, just be careful. These are all monoprotic acids except for the last one. All right, so this H2SO4 is not totally dissociating to give us 2 moles of protons, but it's still considered a strong acid because it's 100% giving up its first proton. But let me just write the definition up here. 100% products, you get full dissociation, full separation, in other words, of the acid. HCl, HBr, HI, nitric acid, chloric acid, perchloric, and sulfuric acid. Okay, how about strong bases? Okay, before we move on, those are 7, right? 7 you gotta memorize. Because not only in this unit, but next unit, it's essential that we know which acids dissociate 100% and which ones actually don't. So, for instance, there's a strong acid, but acetic acid is not a strong acid, it's a weak acid. So it partially dissociates. Once we get through the strong acids, a lot of the unit is going to be focused on weak acids. So don't worry, we'll get to weak acids aplenty in the next couple of videos. But let's think about the strong bases, and there are 8 of them. We are going to use a periodic table just like we did for these first 3 strong acids. Oh, don't worry about why HF is a weak acid. We'll get to that when we talk about trends. Okay? This is just an introduction. For the strong bases, we're going to have what's called the group 1 hydroxides. Group 1 hydroxides. Those are your metals in group 1, and we're going to take 5 of them, lithium through cesium. The first strong base we're going to see is LiOH. LiOH. And let's make it a solid. And let me give you the format in which we dissolve in water with water drawn on top. And, this is a strong base. So we are going to use a full arrow. And just like with strong acids means full dissociation, same thing with strong base, full dissociation. Now, if you're really strict with the definition, bases are substances that can accept a proton. Well, I don't literally see exception of a proton. What's accepting a proton? Well, again, we have to be kind of flexible with the formatting. This is a hydroxide. And when a hydroxide is in water, it's actually this that accepts a proton. OH accepts a proton. That still doesn't negate that this is not the base. This is also the base, even though this is the species that's accepting the proton. So you could think of it as a base is a substance that creates a substance that accepts a proton. Same thing. Okay. I know it's very, very subtle, but all of the molecules that can liberate hydroxide, like LiOH, that is considered a base. And of course, this will go on, and I'm not going to draw an arrow here, but this could go on and it can accept a proton from an acid. And the acid could also be even water. And that substance will accept a proton. I don't want to belabor the point. That's a strong base. So if we go down the group, you have also NaOH. And you have potassium hydroxide, KOH. And rubidium, RbOH. And the last one is cesium, OH. So here we have 5 of them. Okay. We also have the group 2 hydroxides that are strong bases. Group 2 hydroxides. And those are the three of them, the other three. How are we going to start? We're going to start not with beryllium hydroxide, not with magnesium, but calcium, strontium, and barium. It's actually these three closer to the bottom that are the strong hydroxides. Why is that the case? Well, again, we won't go over why, but beryllium hydroxide and magnesium hydroxide are weak bases. They don't liberate that hydroxide like the other three. So let's see. Now, just remember we have to balance. Calcium hydroxide is actually that. And true, when you're able to get this to dissolve, I'm picking my language very carefully, you will get dissociation, and let me double check. You will get two hydroxide ions. So we have Ca2 plus 2 OH minus, and we should put aqueous and aqueous. Okay. This always bothered me that later on we'll learn that calcium hydroxide is not very soluble, but it's still considered a strong base. I think the workaround, for those of you who are following me, is that whatever is soluble will completely dissociate. That's why calcium hydroxide is considered a strong base, even though it doesn't have very good solubility. There's a very, very subtle difference between solubility and dissociation. Let's not go too deep into that. These are considered strong bases, these 8. So we have calcium hydroxide, strontium hydroxide, and, oh boy, barium? Yep, barium hydroxide, group 2. Okay, that's all I want to say for this video. Those are the 7 strong acids you should definitely try to memorize. And these are the 8 strong bases that you should definitely try to memorize. In the next couple of videos, we'll talk about weak acids and bases, and also, at least in I think the next video, we'll talk about conjugate acids and bases. We never really labeled the stuff on the right, these ions. Those will be talked about in the next video.